think what we want to get into today a little bit more, Neil, is this car redesign, the next gen car, right? I got to see it on the AWS reInvent Expo floor in Vegas last year. I know we had it was like a big partnership between AWS and F1. So can you kind of set the stage? What is that?
Yeah, sure. So one of the things, we talked about improving the racing and what Formula One wanted to do. And one of the things that they did is they put out a survey to their fans to say, what do you like and what could be improved? And one of the things that the fans were saying is they wanted closer racing. They wanted to see more overtakes. They wanted to see close battle. They wanted it to be unpredictable.
Yeah.
And at that time, it was the case that actually one team was sort of dominant. There was a problem with the cars overtaking, and that was really hurting the spectacle of the race. So one of the things that Formula One realized is they needed to do something about it. And what they'd previously done is they'd previously asked teams. So they previously said, Formula One being the people who own the sport now, okay, Team X or Team Y, what do you think we should do to change the rules to make better overtaking or better racing? But that sounds like a good idea. But the reality is these teams are so competitive, so driven to win, that they only want to give the suggestion, which is ultimately going to help them. So it wasn't really the optimal way. Yes, there was some rules changed in the past and it did make some improvements, but F1 realized that if they really wanted to solve this problem, they needed to do some of it themselves. They needed to form their own sort of team,
like
to
develop
teams. Exactly. And that's the team that I was helping before joining AWS to try and come up with these new rules to improve, to make closer racing, essentially.
Gotcha. So basically the problem, but what fans were saying was they wanted to see more, when you say overtaking, like the car behind wasn't passing the lead car as much as they wanted, right? Like that's the exciting part of the race. So what did you guys find out? Like what was causing that? And then how did that eventually lead to this, next gen car that we've done?
Yeah. So, first of all, any motorsport, doesn't matter whether it's Formula One or anything else, everybody wants to see close racing. It's,
of course,
it's exciting. Yeah. What basically they need to do was figure out what it was. Well, what it turned out to be is a problem with aerodynamics. Now, aerodynamics is a term that a lot of people have heard about. Turbulence, unfortunately, in recent news with certain aircrafts having problems, turbulence is a word that comes around and it's often usually not in a good way.
Yeah.
But turbulence actually is something that's happening on a Formula One car.
Okay.
And it's probably worth explaining a little bit what that is so people can get a sense of why. The way I think about it is the following. Formula One cars are really fast.
Yeah.
But then how fast they are in a straight line is not really the wow factor. Like, okay, they sound good and they go fast. That is good. But really what sets them apart is how fast they go around a corner to the point that they pull more than 5G in a corner, but they're not wearing a G suit, right? So they're pulling like a fighter pilot, but they're just there with a helmet on, strapped into a car. And remember, they're doing, that corner happens maybe 6-7 times a lap.
Yeah.
And then they're doing it 70 times. So they've got 2 hours of this unbelievable physical exertion because of these G-forces.
Gotcha. And I think that's what you're telling me too. That you have to, bring back to that airplane example, you have to build the car instead of having kind of downdrafts or updrafts like lift on an airplane. These cars have to compensate for the fact they're flying around these corners by having downforce, like to keep them on the road, right?
Yeah. So the example I would give, and here's a follow at home sort of thing, is if you were to put your hands on the desk in front of you, if you happen to be sat down or some surface, and I ask you to move your hands across the desk, you can do it quite easily, right? It's not difficult to do. But if I ask you now to really put a lot of pressure with your hands, push as hard as you can onto your desk and now slide your hands, you should find, one, it's harder to do, right? There's more resistance.
Yeah.
And you're going to generate even a bit of heat.
Yeah.
That's exactly the same analogy, except your hands are the tires of the Formula One car.
Mhm.
And if you don't create this downforce, ultimately those tires, when it goes around a corner, are going to lose some grip and
Mhm.
they're going to slide off or they're going to come off the throttle. Whereas if you can generate some downforce, you're pushing those tires in, it's sticking to the ground, and it's now able to keep going in the trajectory it is. And so that's why they took a trick out of the aerospace, hence the link to aerospace. They took a link out of the aeronautics lift generating devices
Mhm.
and put them on a Formula One car, but just turn them upside down. And so that's why modern Formula One car is full of these little wings.
Gotcha. Okay.
Yeah,
So the little grills kind of in the front and the back are just creating that downforce.
exactly.
Gotcha. Okay. So how do we tie this all together? So how did this kind of explanation of, the downforce, everything else, how does that play into the design of this next gen car and this problem with overtaking that you described?
So if it's just one car, great. You generate this downforce. It can go super fast around the corners. Right. And that's what the team's focus on, by the way.
Yeah.
But it just happens to be that if you are the poor person who's following behind the car,
Okay.
you're going to experience now the wake, the turbulent wake that is generated because all of that sort of momentum and force that's been done to squish that air and push it is now actually being released behind the car and being swept up. A bit like if you're following behind a boat on a lake,
Okay.
and you get behind it and you start to rock or you cross over its wake.
Yeah.
That's happening in water. You can see it, but it's also happening in air, but it's invisible.
Gotcha. So that wake behind the lead car, the following car is feeling it, making it less.
In fact, do we have that? I think that we might have a video.
Yeah.
That first one might illustrate it quite well. Yeah, perfect. So you see that front car, we're using a computer simulation to show the color, to show the air, because it'd be invisible. Like I say, it's blue, but it's obviously not really blue.
Yeah.
And it's pushing off that wake. And you see the car behind, it's now actually going into it, which means all those wings, they actually don't work as well when they're flying into this turbulent wake, to the point that they actually lose about half of the downforce. So that car behind was doing great until it was about 50 meters away. And suddenly it gets into that zone, that sort of turbulent wake. And you hear this on the commentary still, where it loses the downforce and therefore it can't follow as closely. And ultimately it has to back off. It can't overtake, can't follow. That was basically the challenge that they realized. And they're like, right, how do we fix that?
Gotcha. So let me go ahead and take that down. So basically, the problem, like people weren't able to overtake as much because when they were getting close enough to do so, they were losing. I think you'd mentioned it's like a 50% loss in traction, right?
Yeah.
Which is huge when you're going 200 miles an hour.
Yeah, exactly. To the point where, you just literally, and the drivers were saying it, they were on the thing going, I can't overtake, I can't get past.
Yeah.
There were certain things that were created, like this drag reduction system, it's called DRS, where this rear wing flap changes. But that was a very sort of artificial way that didn't really fully solve the problem, and the fans didn't really like it because they saw it being quite artificial. So, basically Formula One said, right, we need to do it. We're going to create our own team. We're going to come up with new car design with the aim that the following car should be able to keep most of its downforce and therefore follow much more closely and allow the great racing that everybody wants.
Gotcha. So our goal was to design a car to make it easier to overtake. We're talking through how we went about solving that problem. Neil, when we went into this first, right, what were some of the things we had to take into account? And like, did we know what like the problem was and how to solve for it right away? Because I assume, if you just focus on the following car, maybe, and design it for that, maybe that lead car that doesn't have the wake in front might be a little bit too, pushed down too heavy because it doesn't work as well without the wake in front. Or like, what kind of things did we have to take into account?
Yeah, so it's definitely that what made it so special is that this had never really been done before, because the Formula One teams didn't need to design two cars. They were never doing this. So it was genuinely like an open area, an open discussion of how do you even do this? And what that really meant was the team had to explore a huge design space. They really had to think, okay, do we want to send the wake over the car? Do we want to send the wake around the car? Do we need to change just the fundamental nature of the way the cars generate downforce? They had to do, and another thing to remember is the cars are not static.
Yeah.
They're not like this. They're coming at each other. They're coming to the side. They're going around corners. So there were so many different scenarios they had to explore. And one of the things they used to do this was, and this is, I guess, the reason that I was involved, is this computational fluid dynamics, because physically making a car is an expensive and time-consuming process. Just one car.
Yeah.
It takes months to build, hundreds of thousands of dollars. You need an engine, you need a driver, it needs to pass safety tests. So it's not realistic that you could design 5,000 different cars and make them. It would just take you like 10 years to do it.
Yeah.
So they needed to do something faster. And so that's where they turned to using computers and using software packages to do numerical simulations of the airflow rather than physically making a car and driving around a track.
Gotcha. So yeah, let's get into that a little bit. What did each team bring to the table here? So you got the F1 side, what were they responsible for within this? And then what did AWS bring to the table to help them make this a reality?
Sure. Yeah. So I probably, sometimes when I speak on this episode, I'm saying like when I was working for F1, and then sometimes I'm saying when I was for AWS. So apologies if I'm sort of blurring the lines a little bit. But yeah, that was a good question. So Formula One, obviously they're the designers, right? They're the ones who are trying to come up with all these different car designs. But fundamentally, because they've gone down the route of doing this numerically, which was, in my opinion, a good idea, one thing that people need to know is that these simulations can't just run on your laptop. In fact, if they could, let's just say theoretically, if you had enough memory and stuff, they'd probably take about 2 years to run one simulation.
Okay.
So we're talking about extremely computationally heavy simulations, which require supercomputers, high-performance computing to solve. And Formula One did have access to some limited resources, but it was limiting their ability because each simulation, the big ones, when they really wanted to study 2 cars and high fidelity, may take 2 to 3 days to run.
Okay.
And they could only run one at once, and they had to wait for it. It was a sort of a bottleneck. So what they specifically said to AWS is, can you help us to unblock ourselves so that we can run these simulations as big and as complicated and as many of them as possible so that we can try and find the best possible car to solve this problem?
Gotcha. So if I'm hearing you correctly, basically there were 3 options. So F1 wanted to design this new car. We needed to test to make, I say we, and this, both of us, F1, AWS, just collectively. F1 needed to design this car to be able to allow for less downforce reduction when a car is overtaking a lead car, right? There were 3 options to do that. They could physically build a bunch of test cars, which you said takes months. You got to pass safety. So you maybe do, 1 a year, 2 a year. You could do normal computer simulations, which requires a supercomputer type of vibe to do this kind of thing. Those could take 2 to 3 days, so one every 2 to 3 days. AWS came in and allowed for greater computational capacity to maybe run one every 10 hours, right? So we went from doing like one every couple months to one every 3 days to, maybe 2 a day.
Exactly. And that really, I think, was a game changer because it allowed them to study so many designs. And anybody who is a designer or an artist, or it doesn't matter, that often the more you can do, the better. Yeah. If someone says to you, you can only do 5, that's it. The likelihood that you're going to find the best thing after 5 is limited. Where if I said you could do 5,000, you're probably more likely to get a better outcome if I give you more chance to do it. So that's essentially what it was. But the key point on that is they wanted to have the ability to do it, but they were also a very spiky customer in the sense that, sometimes one week they would want to run loads of simulations, but the other week they may be actually doing something else. They may be at a track, they may be speaking with teams, and they wouldn't be doing anything. So one of the advantages of the cloud and AWS with pay-as-you-go and on-demand was that they could just pay for the amount they needed to use. So they sort of spiked up, like, okay, I'm going to run loads and loads of simulations for this key meeting on a Friday.
Yeah.
And this is literally what would happen. Meeting on Friday. I need the results by Friday.
Yeah.
And then spend the next week writing a report. So from a cost point of view, it meant they were paying for all those, but then that week when they weren't, it was essentially close to zero. That is far more attractive. You think the alternative to using AWS would have been for them to go and buy essentially a massive supercomputer at probably millions of dollars that would have just sat there idle during that week. Then they were away. So there was there was a real advantage to them having that agility, I'd say, that made for a natural sort of coupling of why we worked together on this.
Gotcha. So F1 brought the engineering insight, the car expertise. AWS brought the speed and kind of convenience of being able to run these faster, get this project done faster, this next gen car.
Yeah, and of course, maybe it's not as interesting to talk about, but there's all the plumbing and the stuff that needs to be done to create a secure and scalable AWS infrastructure. And that's where, professional services, some of our hands-on keyboard consulting team are able to jump in and sort of get them going really fast. So there's all the sort of sexy stuff that we talk about, the simulations, but there's also all the sort of back-end stuff that is needed for any company to have a solid foundation in terms of AWS accounts and all that.
Yeah, absolutely. Shout out to the AWS ProServe team. Those guys handle so much, and I love hearing about what they do. Let's talk about the kind of results from this then. So we ran all these simulations. We eventually came up with a solution. Can you talk us through, one, what was changed within these cars a little bit? Talk about some of maybe the gearhead stuff, what the results were from those changes, and kind of how we've seen that play out in the sport over the last few years.
Yeah, sure. So maybe it's a good time to show that other video, because what we're really seeing here is now what that new car looks like. Now, it depends if you're into F1 or not, and whether you can sort of see the difference. But one of the things that it did was, in the first video, you saw that they were losing about 50% of their downforce. Now, if you look close, can you see that wake of that front car?
Mm-hmm.
I don't know if you remember what the other one looked like, but this one has quite a dip. Can you see how it's like jumped above it? Yeah, can you see that?
See the old one.
Yeah, can you see how it's like smashing into the front nose almost?
Yeah.
Some of it's going above, but a lot of it's going in. If you go to the other one, and we goes back to the beginning, you'll see this. Yeah, can you see that separate? Exactly. So that was one of the fundamental sort of aerodynamic concepts of how do I lift that wake up of the car. And that is not the only way, but that was one of the key ways to do it. Now, the real challenge was the airflow goes from the front to the back.
Mm-hmm.
How do you make sure that as it goes from the front to the back, it's able to be lifted up, essentially over, which is harder than it sounds to do, and required a lot of, whilst also keeping the downforce. Remember, this is a key point.
Yeah.
Yes, you want them to be able to follow, but you don't want them to end up being super slow cars. So there was also a requirement to keep the downforce, which actually was one of the hardest things to do, or one of the harder things to do.
Gotcha. So what were the results of this project? So we focused on lifting it as well as some other things. What came of it? So we used to have 50% downforce reduction if you're a following car. What happened after this project?
Yeah, so it ended up being only 10 to 15%.
Okay.
Which, is a huge difference actually from a driver point of view. You could feel that extra downforce, that confidence to be able to follow. So that was essentially, and then if you want to know, did it actually translate into closer racing? It's a hard one to measure because closer racing is hard to measure. But what we were able to measure is there were 30% more overtakes, which really gave to the engineers. And I have to say that first race of the year was actually quite nervous.
Yeah.
For me, definitely for the people who worked in F1 the whole time, but even for me who was there for some of it, because you think you've done all that work. You've told all the teams, hey, you need to now design a completely new car at quite a considerable cost, time, effort. If you go to the first race and it's no better, then people are going to be like, what did you do? You just wasted all of our money.
Yeah.
So it was good. And I think after the first few races, I remember watching the TV and the drivers and the team principals and the commentators were like, it's so much better, the overtaking now. These rules have been a success. Not just me, but I think a lot of the others were like, "Oh, thank God for
Yeah,
that."
you get holding your breath, crossing your fingers, like please, please let
Yeah.
somebody overtake.
Yeah,
Gotcha.
exactly. So yeah, there was absolutely positive outcome, and you know, of course, most of the credit goes to Formula One, but I think we did play, a good role in giving them the best possible chance of getting to that point in the timeline that they had.
And I think another cool aspect of this project that you had mentioned to me is like most of the time with these car redesigns are coming from the teams, right? Because those teams are looking for ways of like, how can we make our one car faster or better or quicker around the turns? Whereas this was a centralized effort from F1 as like the league saying, how can we make all cars better? I'm sure that kind of added to the pressure too, right? Not only was this nerve wracking from that point of view of like, I hope this works, but also this was kind of the first time something like this had been done in general,
Yeah,
right?
I mean, there's Formula One said that this project was one of the most revolutionary, and it was in a way because, like I said, Formula One teams hadn't done these big two-car simulations, so Formula One had to do it. I won't get into the boring details, but because they were mainly using CFD, the fidelity of the simulation was actually very groundbreaking. Like the maths behind it was sort of quite cutting edge. So on many levels, it was quite an ambitious project. And I think some people at the beginning thought maybe it wouldn't, work, but it did. And I think that's, credit to them.
Yeah, I think it's really cool. I could spend a while talking about it. I mean, and the fact that we went from 50% to 15%, you said drivers were coming off the track too, saying that it felt better, right?
Yeah, exactly. And like I said, it was a good example of the power of AWS, high performance computing, that sort of flexible access to give it. I think without naming names, a lot of customers saw that and it inspired them for their own industry, whether it's aerospace, automotive, motorsport. We definitely saw it resonate. And again, going back right to the beginning, what was the point of this partnership? It was for us to help Formula One, but it was also for Formula One to help us to mature our products, our service, the working backwards thing you often hear. And it did. It was absolutely the case. They told us, hey, we love this, but could you do better in this area? And, that's exactly what we did. We sometimes took feedback, iterated in our products, and now that's helped other customers to be able to use that. So I think it's been a win-win for both sides.